So today we're going to officially be starting the trig unit, but before, as part of the trig unit, there's some things we need to review in terms of angles. So the first thing I want to talk about is just angles in general, and get some terminology down. So I have at the top of the page here some angles drawn, and the initial side is where the angle originates from when we're talking about a rotation. So if I were to draw what's happening here in this first, I would say, okay, my rotation is originating from this initial side and it's terminating at the terminal side or ending. And notice that this angle here in part A is an acute angle. And in part B, the initial side and rotating around the vertex to the terminal side, this would be an obtuse. And the other, so notice here, however, in part C, I've got the initial side up here and then terminating along the horizontal. And in part D, what's happening if I go like that? Well, the difference here, remember, in terms of angle measure, and we're used to measuring in degrees so far, is it's a positive angle measure if we're going counterclockwise, and it's a negative angle measure if we're going clockwise, which goes along with, if we talk about quadrants, you got quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So the quadrants go up as you go counterclockwise, same with angle measured being positive, goes counterclockwise. Now we're mostly going to be drawing angles in standard position, which would be like A and B, where the initial side corresponds to the positive x-axis. We'll have the vertex at the origin 0, 0, and angles that open up in counterclockwise direction have a positive angle, and angles that open clockwise would have a negative angle measure. And so yes, so here, if I wanted to write in, this would be negative. And so here's some questions for you, like for A through E. This angle opens up in a clockwise direction and its terminal side is on the positive y-axis. Well, what angle is that? And so again, so what I'm asking is if it's, we're talking all in standard position here. So if it opens in a clockwise direction and terminates on the positive y-axis, what would that measure be? Well, it would be negative 270 degrees. So you want to fill out A through E based on these descriptions here. Now, if we want to, the next page is going to be developing the idea of a different way to measure rotation other than degrees, and that's going to be radians. And so if we look here, I'm going to have you do a few problems to develop the idea, but in general, we're going to see that radian measure is how many radius units per intercepted arc. So let's think about that here. So if I were to draw, let me just draw a circle here. If I were to draw a circle, and remember that an angle that originates at the center of a circle is called a central angle. So if I call this angle theta here, theta is going to be a common variable we're going to use for an angle in this unit. Then, of course, these lengths here are the radius, and this here is called the intercepted arc. It's been formed by the central angle, and we label that as S, the arc length S there. Well, by definition, radians is going to be equal to, or radian measure is equal to, how many radius units per intercepted arc. So for example, 1 radian would mean that the radius of this central angle equals the arc length. That's what 1 radian means. And radians actually have no units. So unlike degrees that have that little symbol, when you see, say, an angle had measure 2 radians, you wouldn't say 2 radians, you just say 2. And it's when you see that you will be expected to know that that means radians. Okay, so let's talk about conversions. So, and this is getting really at G on the front of the 3rd page. So when we look here, it is saying that, so the measure of a central angle associated with an arc length equal to that of the radius circle is exactly 1 radian. Then this is how a radian is defined, so that's just what we talked about. Given this definition, how many radians are equal to 360 degrees? So if we're talking about the entire, so again, let's go back to the definition. It's intercepted arc divided by r, the radius. Well, if we're talking about the entire circle being the intercepted arc, which would be the case with 360 degrees, then that length would be the circumference, which is 2 pi r over r, or 2 pi. So in other words, 360 degrees is equal to 2 pi radians. That's going to be where all our conversions are going to come from. So if I say how many radians are in 180, well, if I divide both sides by 2, I see that 180 degrees is going to equal pi radians. How about 1 degree? Well, from the equation above, I could divide both, let me get a better pen here. I could divide 180 degrees by 180, and both sides by 180, and I get that 1 degree, oops, get an eraser here. So we get that 1 degree is equal to pi over 180 radians. Similarly, if I want to go see what 1 radian is, I could go back to h and divide both sides by pi, and I get that 1 radian, again, you don't usually use units, but just to show you, 1 radian is going to be 180 over pi degrees. So what does that mean? Well, if I have degrees and I want to get radians, I can multiply by pi over 180. If I have radians and want to get degrees, I can multiply by 180 over pi. So for example, if we go down here, I have 36 degrees, and if I want to get it in terms of radians, I can do, okay, 36 degrees times pi over 180, and simplify that to get pi over 5. And so we can convert between the two. And then, so similarly, if we have radians, we can get degrees by, let's take pi over 9, by multiplying by 180 over pi. So pi over 9 radians times, like multiplying by 180 over pi, you get the fact that this is 20 degrees for G. Now, a hugely important new term for you is coterminal. And angles are coterminal if they originate, so if they have the same initial side and same ending side or terminal side, but differ in measure. So for example, if I was talking about 120 degrees, let's see where 120 degrees is. 120 degrees is going to be in the second quadrant, so this would be 120 degrees. Well, that's coterminal to an angle that, again, same initial, same terminal side, that would be coterminal to this angle, which would be negative, so if you do 360 minus 120, what's the negative version of this? So this would be the same as negative 240. Or we could say another 120 is also coterminal to, if I were to go a full rotation, plus 120. So 360 plus 120 would be 480. So it's also coterminal to 480. It's also coterminal to, if I were to do one full negative rotation, and then back to the same spot. It would be negative 240 plus negative 360, which would be negative 600. So there's infinite positive and negative angles that are coterminal to any given angle. And notice they are multiples of 360 away. So what about something in terms of radians? I'm not going to convert to degrees and then back to radians. Instead, they'll be multiples of 2 pi away. So for example, pi over 6 is, and you'll get to know pi over 6 quite well, pi over 6 is 30 degrees, or it's in the first quadrant, but it does correspond to 30 degrees. So if I've got pi over 6, well, a positive angle that's coterminal to that would be 2 pi, because that's one full rotation, plus pi over 6, which is 13 pi over 6. And then I could do another rotation out, which would give me 25 pi over 6 that it's coterminal to. In terms of a negative angle that it's coterminal to, well, it would be, so we're thinking of pi over 6 minus 2 pi, or in other words, negative 11 pi over 6. And then you could add another negative 2 pi to that to get another negative angle it's coterminal to. Again, there's infinite positive and negative angles that any given angle is coterminal to. But my point with part C is don't change it to degrees, finding the coterminal, and then back to radians. You can do this all in terms of radians. It's going to take some practice getting used to this new way to measure angles. So after you work through these problems, I'll talk about one last thing for today, which is area arc length, which we've kind of hit on a little bit, and area of sectors, which I believe you did last year in geometry, but it's worth reviewing, and to also talk about it in terms of radians. Okay, so you're finding in this, I'm asking you to find two things. I'm asking you to find arc length and to find area of this shaded sector of a circle. Now, in terms of arc length, we're going to work off the definition of radians, which is that theta, in terms of radians, the measure of the angle theta is equal to S over R. So I can find arc length by multiplying my angle measure in terms of radians times the radius. So arc length is going to be my angle in radians times radius. Now, in terms of finding the area of a sector, well, remember, you can find it as a ratio of the total area of the circle. And how do I do that? Well, I think of what is the ratio of my angle to what would be the total angle of the circle times the area of the circle. So that you can do this both in degrees and radians. In degrees, I would say, okay, my area is equal to, well, my angle measure in degrees. So again, this is if it's in degrees. So angle measure in degrees, so I'm going to say area in terms of degrees, over the total area, of the total angle, of the angle if we were talking about the entire circle, which would be 360 degrees. So what fraction is my angle of the total angle of a circle, which is 360 degrees, times pi r squared. So if you have it in degrees, I would use that. However, if you have area in terms of radians, I wouldn't change it to degrees. Instead, you're going to compare your angle in radians over the angle if it was the entire circle, which would be 2 pi, times pi r squared. And notice the nice thing about this formula is the pi's go away, so it's really 1/2 theta r squared, which is nice. Okay, well, there's a lot to work with here, you please work through the problems. Radian, again, it's going to take a while to get used to radians and for it to come naturally instead of always kind of changing it to degrees. But I will post my solutions, which hopefully will also help you. Good luck.